Buonasera, buonasera a tutti gli amici di GiovedìScienza, buonasera a Riccardo Zecchina. Riccardo Zecchina è professore.
Good evening to all our friends from GiovedìScienza. Good evening, Riccardo Zecchina, whom I would like to thank for being here. He is a full professor of theoretical physics at the Turin Polytechnic, and he is currently moving to the Bocconi University in Milan, where he already teaches. But he has spent most of his time abroad, mostly in Boston, as Professor Gorlier used to say. He was the one who was the English language specialist in Fruttero and Lucentini's book, but he worked in the U.S. universities. He's one of the most brilliant theoretical physicists, not only of Italy but of the world. And last year, he won the American Physics Society Prize, which is very important for theoretical physics, which is the Lance Honsager. And he is the first Italian to win it, and he shared it with Giorgio Parisi, who is another important theoretical physicist. Mentioning Parisi, you will have realized that what Riccardo Zecchina studies is complexity. Those phenomena which are difficult to understand using traditional tools of physics, and quantum mechanics is even included amongst the traditional tools. This evening, we will be talking about these things, talking about deep learning. That is to say, we mean a meta-learning process. That is to say, learning, but by learning how you learn at the same time. At least I think that is what it is, if I understood correctly. And it is a revolution which will change our lives. Thank you. Thank you very much. I would like to talk about is what computers do today. I would like to talk about the ethology of programs. That is to say, how programs learn how to learn and how they pass them on to increasingly complex programs. What is happening, as many of you know, is that there is a major explosion. There are data everywhere, social data, internet, but also physical data on materials, biology data, an explosion of data. This explosion is so big that we don't know how to process them. And this is where we have the need to use new tools, those of artificial intelligence, AI. Deep learning is the tool which has revolutionized research, and in the years to come, it will also change society. I'm going to bring forward something that is to say that 80% of all jobs are services, and these machines are able to carry out this work, and their performance levels exceed the human ones. So it's a good idea to understand what we're talking about, and also to see what the interesting and deep aspects of progress are, and at the same time think of how we have to reorganize our society. I would like to tell you what deep networks are without using any mathematical formulas, and see when it happened. Because in fact, for decades now, we've been talking about artificial intelligence, but up to about 7 and 8 years ago, nothing much had happened. So it is a good idea to understand what this major change has led to. Before I give you examples, I would like to premise what I'm about to say, and I'm saying this for students, and I was very pleased to see them here. We're used to seeing science according to Galileo's method. That is to say, there's a theory, there's a prediction, there's an experiment, there's observation, and the theory can be falsified or proved. This is what led to the Industrial Revolution and to major progress. The last triumph of physics in traditional science was Higgs boson's discovery. There was an enormous accelerator, there was a theory, there was an experiment, and we managed to identify Higgs boson. Major progress, major step forward, fine. But or I could also say, for example, with an atomic microscope, we can photograph molecules and the bonds amongst the atoms, and this helps chemists in an extraordinary manner. However, over the past 400 years, part of science has not progressed. To a degree, it has remained stagnant. There has been progress, but not at the same rhythm of basic science. We're talking about biology, life science, medicine, and social and economic sciences. Many other things too, but this is what I'm going to talk about. In fact, the traditional scientific method has a number of problems. To give you an idea, when we're talking about complex systems and therefore data, say we're talking about the brain, we're talking about an object that has 10 to the power of 10 neurons, and this is connected to 10 to the power of 4 synapses per neuron. If we think of DNA, we have 3 billion base pairs, so that's 25,000 genes. And if we think of the financial market, which I know nothing about, but the number of transactions on one liquid asset in 1 month is millions per month. So processing this data is not simple. It is no longer the issue of having a model, an experiment, and proving a theory. Things have changed because what has happened is that there are a lot of data that come from very different sources, and the problem to moving from data to the model is a very difficult problem. In fact, in Newton's case, if I measure the attraction between two bodies, I can see that it is indirectly proportional to the square of the distance. But if I want to understand how a cell works or a brain, then it becomes very complicated. First of all, there is no one theory that is compatible with observation, and then the moving from data to models is very difficult, and this is where computer science comes in. So this is the methodological novelty, and this is changing the way in which we produce science, if you'll allow the word. In the 80s and 90s, there was a lot of work and a lot of interest on the artificial neural systems. However, as from the 90s, interest declined because basically what happened was that performance was not so good, data were not enough, there was not a lot of biological information, so we lacked the raw material to produce innovative algorithms. What has happened, thanks to the young people who are present here, around about 2005, they pushed the market to produce ever increasingly powerful computers for games. As well as the CPUs, they used also a GPU, which is the graphic processing unit, which is a part of the computer which is used to process images. And what happened? Around about 2005, scientists realized that they could use the GPU for very cheap calculations and very fast calculations. Suddenly, hundreds of thousands of scientists, for a few $1,000s, could have an extraordinary computer. At the same time, in the meantime, technology developed, started producing high-quality data, internet circulated data. We'll see some figures which are absolutely stunning. So around about 2005, 2006, artificial neural networks were once again competitive. And around about 2008, 2010, they were better than any other machine learning method on the market. So currently, if you want to process images, if you want to translate a text, you use, without knowing maybe, deep networks. So you might, maybe unbeknowingly, but that's what you will be using. To give you a historical perspective, in the 20s, here you see computers. It was people who calculated. This was a computer in World War II that could multiply 300 numbers per second, something ridiculous. Now, what happens today is that a youngster is sitting on a chair and has an object like this in his or her computer, a GPU. So you see that the approach has changed completely. Now, the networks I'd like to talk about, to a degree, draw inspiration. I don't want to have a parallel, but they, in fact, refer to the visual system. When you have a signal, it goes to your eyes and it is processed at different levels of the brain. There's the V1, V2 area, and so on and so forth. What happens is that as the signal moves from one level to the other, the neurons learn how to recognize different features of the entry signal. For example, the V1 area will tell you if there are vertical lines, for instance, while in the V2 area, it'll tell you whether these vertical lines are positioned with certain angles or not. As you go further into the brain, you make up what are called features. There is a hierarchical organization which is used to process images, and the deep networks draw inspiration from this. This is evolution. Evolution puts things rather randomly, but then it builds. If we were to plan it, we would probably position the various areas in a linear manner, but in fact, it goes roundabout. So the deep networks take an image and reprocess it, trying to extract features, geometrical features, which are increasingly complex. For instance, there's a first layer with an input which tells you if in the image there are vertical, horizontal lines, and then as you go on, there are increasingly complex features. What is a deep network? Well, a deep network is something like this. Here you have an input, which could be, say, a photograph. Every circle is a pixel of your photography. The signal goes from left to right. Here there's an input. There are 01 pixels. They send a signal according to these lines, which we would call synapses in biology, although it's a misnomer. They send signals to intermediate layers. These intermediate layers process these signals, and they go on. Each single unit, each circle, represents a neuron. Again, comparing this to neuroscience. It takes all the input and emits a signal which tells you whether the sum is above or below a certain threshold. So what do these deep networks do? This is the largest deep network which I was able to put on a slide, but they're not so simple. The first layers are feature extraction layers. They process information, extracting increasingly sophisticated information, while the last ones are the ones which associate features to classes. For instance, the networks which are used today can tell you whether within a photograph that can have thousands of objects that there is a cat. Just to give you an example. So the last layer, the output, tells you, yes, there is a cat, no, there isn't a cat, or gives you a list. We'll see what this means. What I'm interested in is to show you that this network contains a number of connections, real connections, which is of the order of magnitude of 100 million. And to learn, to help these or get these networks to process the data according to our needs requires modifying a large number of parameters, which is roughly 10 to the power 7 or 8. So it's a very complicated object. Once again, you have to imagine that you have 10 to the power of 8 objects like this, and it is clear that there is a very strong analogy with what happens in the brain. That is to say that the connections we're talking about, these weights, are the equivalent of synapses inside a neural network. And this is what gives us the opportunity to compare them linguistically. Here, I've drawn them with blocks because to draw all the lines would be too complicated. The idea is, say you have a photo, the input for a computer, a photograph is but numbers. And then what happens is that as you progress, there are layers that recognize it. We'll see some of this. And then there is the learning phase. But what I would like you to understand is that these networks are not hand-programmed. It's not that we write a program that tells the network what to do. Later, the networks learn from data. So we only have a program that makes the network compatible with data. These are artificial animals that are learning from data. For instance, you may have a first layer which recognizes whether there are vertical slanted lines or whatever. The second hidden layer will recognize if there are circular objects or particular angles. The next one starts to combine the features, and in the end you have the opportunity to combine the information and associate it with the output. So, for instance, if we have put in a certain photograph, we are then able to identify the person. Very rapidly, for the students who are here, I would like to say that this is called a pre-processing, that is to say, a preliminary processing of information with 3 different modalities. The first one is the one that uses convolutional layers. I'm telling you, because sooner or later you're going to read about it, that are basically networks that automatically implement if you have a photograph where there is a cat at top left or bottom right, it makes no difference. They're very efficient systems to extract information of this type. But what these networks do is that they compress information. In other words, given a photograph, the network tries to throw away all the redundant information, tries to identify features so that it is possible to recreate the initial information, but with fewer data. This is how you have to imagine the deep layer. You have a layer, an input, say a photo, then there's the identification of the geometrical features, then it's put together, and in the end there's a network that associates the image to the person. The interesting thing is that you could start asking yourself. Now, let me imagine that I give this photo to the network. When I have trained the machine on millions and millions of images, and I go and see what the output. For example, it tells me that the first neuron is particularly active while the others are less active. I don't know just now. But let us presume that you do this. What we can do is that to a degree, we can amplify the effect of the input on the output. For example, if this neuron is very active, I will try to modify it so that it is even more active. So I try to change the input so that the output signal is even stronger. If you do this, the image becomes this, the one to the right. This is the way in which the network sees the image. It has broken it down into lots of geometrical features, and this is the image that the network uses. So this is the passage. This is something that we do. We don't know exactly what we do, but to a degree we do things such as these. So when I'm talking about geometrical features, you have to imagine that the network, through all these processes of data processing, is able to see this breakdown into elementary parts. This, at this point, can be calculated. It's made of colors and lines, so it's much easier to intervene and associate these other characteristics. These figures always hit me every time I see them. Every day, people put about 800 million photos. Every photo is sent through these convolutionary networks. So these networks are learning. They're learning how to recognize images. They use this information in a massive way. So this is what data explosion means. Every day there are hundreds of millions of images that are put in on Facebook. Facebook, which is an enormous artificial intelligence laboratory, takes this information and use interfaces with the deep networks, and day after day they learn how to recognize and to do lots of things. We'll see some examples. If we talk about cars that are self-driving or medical imaging, augmented reality, so on and so forth, all things that happen thanks to this system. This is something amusing, because now, which I'm going to show you, because it gives you an idea. A useless application of deep networks, which helps us understand what is happening, is that of using them to paint over some photographs. Now, let us presume, say that you're using a deep network like this. First, you give it a Van Gogh painting. The network used for these pictures has 19 layers of this type to extract features with millions of these squares. They recognize features on all the internet images. Facebook uses them, for instance. Now, you can give the network a Van Gogh picture. They will identify a certain area where there are neurons that will be activated according to the chromatic and style characteristics, while others will react to the geometry. So, there are parts of the network that will tell you whether there are circles, lines, or whatever, and others that activate according to the color combination, the stroke of the brush. Here you have Van Gogh in input. We have a network that memorizes the style. Then you give the network a photo, and they have geometric. This picture has style and lines and everything, but you can modify the photograph so as to maintain the geometry. So we want the houses to remain houses, but the artistic styling will be close as possible to Van Gogh's. So, first you give them the picture. Then you give it one photo, and then you modify this photo so as to preserve geometry, but also to preserve the style. Let's see what happens with a few examples. This is when you input Kandinsky. Bit abstract. Well, it's Kandinsky. It becomes the interpretation Kandinsky style. This you recognize as Munch. This is Van Gogh, very beautiful. And you can guess with these squares, it's Picasso, beautiful Picasso painting. I enjoyed preparing two ad hoc ones. This is Turin, but then first I gave the network Van Gogh, then I put the mole of Turin and I Van Gogh'd it, so to speak. I also took a photograph of Bianucci's and reinterpreted it again as a Van Gogh. In one case I gave one picture, and so you see the stars are brought out, and the other one is a self-portrait, and you see there is a wonderful Bianucci self-portrait. Now, you've probably understood what has happened in this system. The reasons why I showed you photos simply because we are visual beings. We see things and we see them, but in fact there are applications in very many different fields of physics or chemistry or whatever. But another area which is easily understood is speech recognition. These machines are able to understand the deep speech. Here you can see a very short example.
Fabulous futuristic submarine, the Nautilus, that conducts an underwater campaign of vengeance against his imperialist oppressor.
Quindi vedete che quella rete lì ha imparato a tradurre in tempo reale il parlato. E quindi diventa.
Here you see, for instance, that network has learned how to translate speech in real time. So you can write what we hear. You shouldn't be surprised because you have this app in your mobile. This is slightly more advanced, but in your mobiles you can already send written short text messages which you have dictated. But the networks are not only able to understand what they say, but also to translate it into another language, following which they're able to synthesize a voice in the other language. Not only that, they're also able to reproduce the timbre of the voice, the color of the voice. It seems like a science fiction. I speak in a mic, and my voice will be speaking Chinese, Mandarin.
In a few years, that we'll be able to break down the language barriers between people.
数年后，我们希望能够打破人们之间的语言障碍。
Allora, questo esempio, questa era una conferenza di machine learning tenuta in Cina.
So this example, this was a conference of machine learning held in China. That's why there was an applause. And if you notice, the sound of the voice was the same as the one of the person who was speaking. This was, I think, a Microsoft application which was created last year, so you can imagine what will happen in a short time. You mean that our foreign secretary will be able to speak English? Yes, with his own accent. Now, what is happening here? Let's try and understand. Using an analogy with images, let's try and understand the potential of this system. Now, if we give a trained deep image the information, this is what the machine will give us. Now, imagine that you are visually impaired. For a visually impaired person, when they connect to a computer, they have a device that reads the text and summarizes and synthesizes with a voice that tells them what it is. However, when a visually impaired person meets an image, that's when they get silence, because they're not able to do anything. And Facebook has already implemented this, the computer can tell you what's in the image. This seems to be very simple, but ImageNet, this network, can have up to 20,000 different objects in an image, which means that the potential is enormous. For instance, if you have the picture of a shop, here you have all the objects quite correctly. If, for instance, you give the network a road, the network is immediately able to tell you that there's a road, that here there are other cars, the cars are parked, there's another building. This is given as sand to the left. No one's perfect, but it's not sand. But the network is able to take an image, segment it, to detect all the objects that are within it, and communicate results. It's quite clear that this is how the self-driving cars work. There are some cameras that receive images, and then you need a computer which in real time can tell you what's there. Now, clearly, this type of operation is not only limited to images. There are current and short-term applications, as I mentioned. That is to say, there's object recognition within images, speech recognition, but above all, data analysis in molecular biology, medicine, economics, to infer causal models. In material science, to synthesize them, there are any number of applications. Let me give you an example. One of the problems that you have in neuroscience is that you can't understand, you can't have the clear picture of connections inside the brain, how neurons are connected. So what we did is that there is a very famous project, which is called Connect-On project, where we take, well, the idea, it has already been taken. You took a mouse cubic millimeter, as the cubic millimeter of a brain of a mouse, then you take a photograph of this cube, you take a photograph, and then you take a few nanometers off, and a second photo, and so on. And then, at that point, you have accumulated millions of photos, or maybe billions, and you would, on the basis of these photos, you would like to see how the neurons are connected, compare different species, and so on and so forth. The problems is that it is 10 to the power of 15 voxels, which are 3D pixels, and it's a very difficult problem. That's a million billions. And what do you use to try and understand how you can recreate this. You use deep networks, so you understand that this is an example of the new scientific method, how you go from data to the model. It requires enormous computational power. They learn from data. It's not something that we can program them for. I spoke about applications in medicine. These are the ones that are short-time ones. There are projects everywhere where you use machine learning to order biological data. This is particularly true in the US, but also now here. And for instance, the US FDA has recently approved a deep network as an instrument of diagnosis. But this will affect all of us. And in particular, early diagnosis of cancer is one of the most interesting areas. Let's try and make these objects come alive. They can modify their behavior, they can learn how to learn. This is a game that many of you will have seen. It goes back to 2012, so it's relatively recent. And here you can see how a game is learning. I can't remember the game, but I'm sure you recognize it. This is the game. It's a very old game. What the network sees is just the screen, and with the screen it sees the points or the marks, the score, and it learns how to move the racket, and you have to destroy the world. Now you see that slowly, initially it made lots of mistakes, but slowly it starts to improve. And here you see, although there is a certain degree of decision, it catches the ball every time and destroys part of the wall. What happens after 600 episodes? At this point, the agent finds and exploits the best strategy of tunneling. And here you see what's happening? The network discovers this, and in its next move, it sends it back on top. It's discovered a strategy. It's discovered that it's very convenient if you send the ball up against the other side of the wall, it will pull it down or destroy it much faster. Now, the relationship between games and computers is very old, well, at least since we've had computers. Many of you will remember in 1999 when Deep Blue, the IBM computer, beat Kasparov at chess. And Deep Blue didn't use deep networks. It didn't use these ones, but used brutal force, so to speak. Why? Because in chess, every time you have a move, you have about 20 possible alternatives. Now, the decision-making tree grows by a factor of 20. If you have an algorithm, a program, which is able to explore this tree, avoiding useless areas, it's possible to see which is the best possible move. And this is what IBM did in '97. Currently in your mobile you have this program which will beat any human being. Recently, there was a game that was considered that it couldn't be attacked by machines. It's the game called Go. I don't know if you've ever played Go. It's very simple. There is a grid, like drafts, 19 by 19, and then there are some white and black drafts. But a white one that is surrounded by a black one is captured by the one playing with the blacks. And this is how you work. The game finishes when one of the two players controls at least 50% of the board. So if they control 50% of the board, it means that the black one, say if it's the white one, cannot position it in any way. It's not easy to know whether you control 50%, so it's always very complicated to decide when you've won. This game was considered, I don't know if you can see it here, that couldn't be run by a computer because at every step of the game you have about 300 different alternatives. So the tree here of alternatives grows by a factor of 300 every time. The possible moves of this game is 10 to the power of 720, something which is really very difficult for computers. So there was no way to use deep blue for this. This is why it was considered until a few years ago. There were scientific papers until a few years ago, you can't do this and you can't do that. So what has happened is that DeepMind built an algorithm built on a deep network, and instead of exploring this tree, it tries to decide what move. It's an intuitive game. It plays against other networks. So basically, when it is their turn, what they do is that they plays millions of games with other networks that are maybe a bit smaller or whatever, and on the basis of the outcome, it decides which move. This is not a certain decision, it's an intuition, a certain number of attempts, and on the basis of the partial information, not the complete information, it chooses to make a move or not. Now, what happened last year or 2 years ago was that they played against the Go game has world, global rankings and European ones. This was the European champion. That in the world ranking, I think, was the 650th. He tried to play against this program and lost. Right. In the end, he was only the 650th. He wasn't. So what we did was that we got the network to play against the Lisi doll, who was the world champion and who was defeated by the machine. It was this very interesting game that was commented live. And the situation is a bit paradoxical, because if you play with a computer game and the level of the program is very low, that is to say you decide to play chess at a very low level, that is to say that the program that plays against you is very low, and you realize that they're making a mistake. But the opposite happened here, in the sense that the program used very new and innovative moves. This happened nearly a year ago, and now this program is able to win without any problems, because it's learned. It's learned how to play against Lisi doll. So the machine can do it much better than humans. I'd like to show you. So this is a game with perfect information, in the sense that you have a board. There's nothing unknown here. All the players are on the same level. They're a par. If you were to play poker, you haven't got the same information, because when you play poker, the opponent can bluff, which is a form of uncertainty. Recently, the deep networks have won against poker champions. So the development of these strategies is quite stunning. I hope I've been able to give you an idea of the potential. Two more things. The problem is the following. How does learning take place? How do we modify synaptic weights so that the network can recognize images, win the game, translate? Well, the way in which we can do it, and I'm very sorry that I can't show you here the film, is that you choose the values of those connections so much so that the network doesn't make mistakes on those examples. We minimize the number of mistakes that the network makes. But that means that you want to find the parameters, the connections, so that the network does what you want with the data that you input. But this is a non-linear, complicated network that has 100 million parameters. So how can you find the value of the weights? This is a very difficult problem. It's a complex landscape, and it is the object of study of computer scientists, mathematicians, physicists. On this surface that describes the number of mistakes that the network makes, how do you find the minimum number of networks, which also makes it possible for us to make predictions in an effective manner? This is the mathematical problem. This is the slide which I would use as the first slide in a seminar. But if we've understood that the problem is that of finding synaptic weights to get the network to do what it is intended to do and modify 100 million parameters, this in itself is a very good starting point. To conclude, I would like to make 3 remarks. The first is, should we worry about HAI? Should we worry about progress in artificial intelligence? Are we creating monsters? Are we going to create self-conscious machines that are going to replace us? No. We don't understand how parts of our brain work. The recurrent process of awareness and conscience are very far from this. The only thing we've understood is that, unquestionably, the connectome, that is to say, connection is the important thing, but we haven't really understood much more. We shouldn't worry about what is called AGI, which is artificial general intelligence. But AI is just artificial intelligence, which is what I've been talking about, extracting information from data. No, we shouldn't worry about it, because clearly it's a great opportunity. I showed what it can have, what impact it can have on visually impaired people, personalized medicine, early diagnosis of cancer, which from a scientific point of view is a mine of information. But as I was saying, all the fields of science are using these systems, and it is fascinating because at the same time we have an accumulation of data that are increasingly complex compared to the neural networks. They're able to describe what is happening in a brain while it's working. So big data plus the ability to process the data opens a new future. This is a great opportunity. We shouldn't be worried about it, because it can make life easier. But what we will have to bear in mind is that 80% of our jobs are in services. And services are answering questions, things like this. And many of the jobs we have are going to be replaced by machines. Clearly, the fact that you can replace them opens opportunities that will create new types of jobs, but it's not quite clear. It will not be possible to replace all these jobs. One interesting one, a famous economist, Achimura from MIT, 3-4 years ago. You know that economists have a few problems with forecasts and predictions because it's a complex system, not because they lack the skills, but he had carried out an analysis of how the labor market could develop, and his conclusion was that new jobs would replace the old jobs. 4 years later, he wrote a new paper on empirical data where he basically said that he withdrew his statement and said, no, this isn't going to happen. So what we have are machines that are non-independent machines which will help us in new research, because all research is carried out in this way. For example, these are used in the Higgs boson to analyze data. So it is something that is very pervasive. And the interesting thing is that from a scientific point of view, for me, for my colleagues and students, is that there's a lot that can be understood on these systems, and there are a lot of new applications that emerge. So it is essential that the university and research centers should keep abreast of what is happening, because otherwise we will lose knowledge and job shares, because it's an exponential rhythm. The more powerful they become, the more results they give. I hope that this has clarified what we're talking about. Networks, very deep networks. Deep means that it's deep, that there are lots of strata. And the last ones are the ones that associate these features with the characteristics that we're interested in. And this is the way in which this network works. You've also understood the order of magnitude. 100 million parameters. This is what we're talking about. Very complex objects that can be processed with the modern computers, also thanks to games. Thank you very much.